I'm Coach Pete of Math Coach Me. I provide math coaching and tutoring services for students in high school and in middle school, and I also provide free online lessons at my mathcoach.me site. This is the fourth lesson in my trig series on special triangles and their trig ratios. And unique to my approach is the use of Desmos calculators like this one. Trig is a very visual topic, so using Desmos graphics calculators to explore that topic is very useful and very effective. Also unique to my approach is that there is an online version of this lesson at my mathcoach.me site where you can interact with these calculators. So you can set the angles. This is one of the special triangles we're going to look at in this lesson, the 30, 60, 90 triangle. And it has relative sides of 1 and 2 and root 3. And we can see the trig ratios and look up those values here in the table as well. So what's so special about these triangles? Well, one thing that is special about these triangles is you'll find a lot of them on your tests and your unit tests and your exam as well. So that's one thing that's special about them. But there are other things as well. So let's get started and let's find out what's so special about the 30, 60, 90 and the 45, 45, 90 triangles. There's a link to the online version of this lesson in the video description, or you can go to the mathcoach.me site and then go to Lessons. Then locate this lesson, Trigonometry 4, Special Triangles and Trig Ratios. There are two special triangles, the 30, 60, 90 degree triangle and the 45, 45, 90 degree triangle. These triangles are special because they have angles that coincide with the key angles within a 360 degree circle. So let's start with the 30, 60, 90 degree triangle. So the 30 degree, 60 degree, 90 degree triangle typically is just referred to as the 30, 60, 90 triangle. And we can see the relative sides in this diagram here. So opposite the smallest angle is the smallest side of 1, and then 2 opposite the hypotenuse, on the hypotenuse opposite the largest angle, the 90, and then root 3 opposite the 60 degree angle. So one way to remember these is 1, 2, root 3. So just count 1, 2, 3. Put a square root on the last one. Listen, whichever way works for you, you must remember these triangles because these triangles, and specifically their angles and trig ratios, appear on a lot of questions. Okay, questions on homework assignments, but certainly on tests and exams as well. Okay, so they're commonly used, and you just want to be able to draw this out on your test or on a scrap piece of paper while you're doing a test. So those are the relative sides, 1, 2, and root 3. And here's a depiction using the radian measures. So for 30 degrees, pi over 6, pi over 3 for 60 degrees, and pi over 2 for 90 degrees. Looking a little further down here, we can see the ratios for each of these. So the sine of 30 degrees, or sine of pi over 6, would be opposite over hypotenuse, 1 over 2. And that's what we see here. And we see the ratios for each of these. Cos of 30 is root 3 over 2, and then tan of 30 is 1 over root 3. Now, let's talk about this for a moment. This is considered bad form. I purposely left it here with a radical in the denominator. That's the bad form, right? Typically, you would multiply this by root 3 over 3 and end up with root 3 over 3. Okay, so reason I left it this way is I just wanted to leave it in a form where you can quickly, verify, the relative sides and the trig ratios for each. So just as you're reading the SO, CA, TOA for the various trig ratios, just as you're reading them here. So for tan of 30, 1 over root 3, that's why I left it in this form. You wouldn't do that on a test. Okay, We also see the sine, cosine, and tan for 60 degrees. So once again, you can just read them right off of the triangle. So sine is opposite over hypotenuse. So we have sine of 60 is root 3 over 2. 1 over 2 for cosine of 60 and root 3 over 1 for tan of 60. And again, that's just root 3. I left it in that format just the way you would read it via SOHCAHTOA right off the triangle. And we have the reciprocal ratios here. Okay, so where sine of 30 is 1 over 2, or 1/2, cosecant of 30 degrees, or cosecant of pi over 6, is 2 over 1, or simply 2. Okay, so we can see all of the reciprocal ratios for those. Okay, let's explore a little further in this Desmos calculator. This Desmos calculator is set up to display its angles in radian values, so pi over 6, pi over 3, pi over 2, and I can control that size of the angle with this. This is in pi over 6 increments, and I can also see that I've got a theta 2 value that's just multiplying by the conversion ratio of 180 over pi, so I can see the actual degree angle or the degree size of that angle as well in theta 2. So we can use this to explore, what's so special about special triangles. And I've inlaid our 30, 60, 90 special triangle here so that we can see its relative sizes, and we can check that against what our sine ratios are returning as well. So for sine of 30 degrees, I can see that sine of 30 degrees, if I do it with a special triangle, that's opposite over hypotenuse, that's 1/2, and that's what we're seeing here. Cosine of 30 degrees is 0.866. Well, what is that? So I've got a table here that's showing up as root 3 over 2. Cosine of 30 degrees is adjacent over hypotenuse, root 3 over 2. So we can check that for the key angles in our 30, 60, 90 triangle, and we can do that for the 60-degree angle as well. So we can see that for this, the sine of 60 degrees is 0.8666. That's that root 3 over 2. Sine of 60, root 3 over 2. Okay? Now, just want to explore this concept here, and that is, this is pi over 3, or 60 degrees. Let me move that over to 120 degrees. Okay, so that's our next 60-degree increment. So for this angle, 120 degrees, the cosine of that is negative 1/2. Now, let me go back to 60 degrees. So for 60 degrees, cosine is 1/2. For 120 degrees, the cosine is negative 1/2. So same ratio, and this is a topic for another lesson, okay, why that is, right? And it comes clearer once we begin to get into the lessons on graphing our sine and cosine and our various trig ratios. And I have another lesson on using the cast rule, which tells us, which basically is an easy tool for determining whether a ratio is going to be positive or negative. So just to preview that just for a little bit, what is the cosine of an angle? Well, the cosine of an angle is the adjacent side. So for the cosine of 120 degrees, well, you actually don't measure the ratio from the complete angle. What we're going to find is that, for every angle beyond 90 degrees, the reference angle is used. The reference angle is the one that is adjacent to the x-axis. So this is actually, for 120 degrees, this is our reference angle, 60 degrees. And that's why we can read the cosine of 60 degrees is 1 over 2. But why is it negative? Well, the cosine is the adjacent over the hypotenuse, and our adjacent value is actually, on the x-axis, negative 0.5. So negative 0.5 over 1, this is a unit circle with a radius of 1, negative 0.5 over 1 is minus 1/2 or negative 0.5. Okay, let's continue on. And just want to draw your attention, there is a practice activity here, and there's a number of questions you can try, and there's an answer key as well. But the point here is that you do not use a calculator for this practice activity. You do want to learn these special triangles so that you can sketch them out, on the side of your test or on the side of a test question. So basically, this practice activity is to draw the 30, 60, 90 triangle, label all the angles, the relative sizes, and then answer all of these questions without the use of any calculator. The other special triangle is the 45, 45, 90 special triangle. It has equal sides, equal relative sides of 1 and root 2 on the hypotenuse. And of course, 45 degrees and 45 and 90, and the equivalent pi over 4, and pi over 2 angles. One thing that's special about this is, like the 30, 60, 90, its 45 degree angle bisects the each quadrant of a circle. But what's really special about this is, like the 30, 60, 90, you'll find these trig ratios, and you'll find these angles in a lot of questions on your tests and quizzes, and on your exams as well. So let's take a look at some of these trig ratios. We can see that the sine of 45, applying SOHCAHTOA, TOA, would be sine of 45 would be 1 over root 2. Cos of 45 is also 1 over root 2, and the tan of 45 would be 1 over 1. I've left these ratios in a fractional format, just as you would read them, just for convenience, okay, just to match up to those triangles. Like the 30, 60, 90, you want to be able to draw this, okay? So when you're writing a test, when you're taking your exam, you want to be able to draw those and draw those relative lengths. The easy way to remember this, just like counting, the other one was 1, 2, 3. This one is 1, 2, 1, 1, 2, 1, 2. Of course, same size, right? So 1, 1, and root 2, okay? Another way to remember this is apply the Pythagorean. Okay, so c squared is equal to a squared plus b squared. A squared is 1, b squared is 1. 1 plus 1 is 2. C squared is also 2. Okay, so remember these triangles, be able to draw them immediately. And even though I've left them this way, do not leave them this way on your test. Okay, so for cos of 45 or sine of 45, I'm reading these as 1 over root 2, but you'd multiply those by root 2 over root 2 to basically get that radical out of the denominator. Okay, let's explore this a little bit more in this Desmos calculator. This Desmos calculator is also set up to show radians. We've got pi over 6 and pi over 3. This is pi over 4, pi over 2, 3 pi over 4 when we're talking about our special triangle and our 45 degree angles. And I've got a conversion of that. So theta 1 is in radians, and theta 2 is multiplying theta 1 times 180 over pi to convert that into a degree. So when I start to move this around, start at 0, 45, 90, and then we have 135, 180, 225. So this is also one of our 45 angles. So one thing that's special about the 45 degree angle and our 45, 45, 90 triangle is those 45s bisect each quadrant. Okay, so you'll find one of the versions of the 45 degree angle within each quadrant. Okay, and just going on, we've got 270 degrees, and there's, went a little too far. There's our last one at 315 degrees. Okay, let's start in quadrant 1 with our 45 degree angle, or our pi over 4 angle for theta 1, 45 degree angle, expressed in degrees. So when we look at the trig ratios, and you can see I've also inlaid our special triangle here so I can quickly check the relative sizes as I'm applying SO, CA, TOA. So for our sine of theta, okay, for 45 degrees is 1 opposite over hypotenuse, 1 over root 2. And we can see that, before I leave that, cos of 45 degrees, cos of theta in this case, 45 degrees, is also 1 over root 2. Okay, and I can see the same value for both sine of theta and cos of theta, 0.7071 and so on, right? So that I've got this 1 over 2 fraction, seeing that that is the same number. Okay, so that's basically 1 over root 2. For tan of theta, it is opposite over adjacent, and that's 1 over 1. And that's what we see here for tan of theta, or for tan of 45 degrees. Okay, let's take a look at, as we did earlier, this angle. So this is the 135 degree angle. Okay, so that's 45, 90, add another 45, and we arrive here at 135 degrees. So like we discussed when we're looking at the 30, 60, 90 triangle within the calculator, when you are applying the trig ratio, anything beyond 90 degrees, for any angle beyond 90 degrees like 225, you actually apply the trig ratio to its reference angle, okay, the one that is alongside the x-axis, okay? So here's our 45 degree, for this 135 degree angle. And using that, we could see that the sine of 45, just as we did earlier, would be 1 over root 2, and so would the cos of 45, 1 over root 2. And we see that here. However, there's a bit of a discrepancy. For our sine of 135 degrees, okay, it is positive 0.707, or positive 1 over root 2. For our cosine, it's negative 1 over root 2. And as we looked at before, okay, the reason is that within this quadrant, if we apply the sine ratio to this angle, it is opposite over the hypotenuse. This is a unit circle with a radius of 1, so our hypotenuse is 1, right? And our opposite side is basically a positive y number, okay? It's somewhere up here. It's, I don't know, it's probably 0.707, right? That's where it is, right? So the opposite side, the y value is positive, so for our sine ratio, it is positive. However, for our cosine ratio, we're on the negative axis, or the negative x-axis. So cosine of 135 degrees, okay, using its reference angle 45, is the adjacent over the hypotenuse. Well, the adjacent side is on the negative x-axis, so that's negative 0.707 la-di-da, divided by 1, and that's why we have a negative value. More on that later. That's going to become even more clearer as we take a look at the graphs for these ratios. Okay, there is a practice activity here, and there are 6 problems here for the 6 different trig ratios using our special 45 degree angle. There's an answer key as well, but the point here is, like with the previous activity, the point of this activity is do not use a calculator. Don't use this Desmos calculator. Don't use your own calculator, okay? On your test, so you're going to have a whole bunch of questions that say, provide or solve for theta, or provide an exact answer, right? That means don't use a calculator. When you use a calculator, you get funny numbers like this, right? They want this number, okay, 1 over root 2. But of course, you multiply that by root 2 over root 2, and you get root 2 over 2, okay? You never put the radical or leave a radical in the denominator. So lots of questions like that. Some tests you're not allowed a calculator, okay? So they're all going to be based on these special angles, your 30, 60, 90, and 45 angle. So you want to be able to draw these special triangles, okay, like this one. You want to be able to draw the 30, 60, 90, label all the angles, label all the relative sides, and then use that to answer these types of questions. That's it for this lesson on special triangles and their trig ratios. Be sure to like this video and to follow the Math Coach Me channel. This graph here is from our next lesson. This is showing us a sine wave and the interaction between the angles in a unit circle as it rotates all the way around the circle and back, and the corresponding plotted function on the sine wave. So we're going to interact with this graphics calculator in the next lesson and others like it as we explore how to graph the sine function and its reciprocal cosecant function. See you then.